Okay, folks, welcome to my top 10 trig idea video. Let's get started. Okay, the first idea that I want to talk about has to do with angles. So I have my first side, my initial side, and then I have my terminal side, which I could move around anywhere. I can move that all the way around. Now, we're familiar with two rays that have a common endpoint, and we also understand that this would be a 90-degree angle, right? And I could have another 90-degree angle that would make 180 going all the way around here. But I could go around again and again. So 360 degrees is all the way around. Now, we could talk about the sun, okay? And we could talk about the Earth and the Earth going around the sun. How many days in a year? About 360. Okay, so blame the Babylonians for that. Now, when we're talking about angles, we could use obviously degrees. Degrees. Now we know this is 90. Okay, so half of 90 would be 45 degrees. 1 degree would be very, very small, okay? All right. Of course, we could break degrees down into parts, but we're not going to do that right now. Now, another way of measuring, when I say another way of measuring, we can have feet and meters, right? Two different systems of measuring length, okay? We could have inches and centimeters. As a matter of fact, 1 inch is equal to 2.54 centimeters. So anyway, on this particular video, we're talking about different ways of measuring, and we have degrees for measuring angle. We also have a radian. What in the world is a radian? A radian is a unitless measure of an angle. Let me explain that. If you take a circle, and you just measure out the radius of a circle, right, that long, and then you travel on the arc of that circle, that same distance, whatever that is. So again, I started here, I ended here, I start here, I end here. Now, I'm going to put a ray right here, okay? Everybody see my angle now? Now, this angle right here is 1 radius on the arc. It's also called 1 radian. 1 radian. Now, if you played around with this and you went another radian, and then you went 1 more radian, you'd almost get to 180 degrees. Almost, but not quite. Matter of fact, it takes 3.14 radians to get all the way to 180 degrees. Okay? So that tells us something. Pi, or 3.14 radians, pi radians, I'm just going to put an R there, is equal to 180 degrees. And that is just like we talked about here, where we have a little conversion formula, so we know how to go between the two different measures. Now, so if going all the way around, halfway around a circle is pi, what would be halfway around a circle? Halfway around 180, right, would be 90. So that's half of pi, or pi over 2. That is all that means. That's all it ever meant, and that's all it ever will mean. Now, there is a little bit something I need to add to this little part. It's called arc length. Arc length. Let me give you an example. Here's a circle, and I want to know how long this arc is. Okay, this arc of the circle. Well, good news is let's just say that arc was 2 radians, okay, this angle is 2 radiuses long, and let's say a radius was 5 inches or 5 meters. Well, if it's 5 meters as a radius, and this is 2 radians as angle right here, okay, it would be 2 radiuses, or 10 meters, 10 meters. Now, this part of the circle, the part on the circle, is called the arc length, that's S. This guy right here was a radius, which is R, and then here's my angle right here. I could use theta for my angle. And here is the relationship. The arc length on any circle is equal to the radius times the angle in radians. Now, I'm going to use that R, okay, and eventually I'm going to drop it because y'all are going to be so tired of me talking about it. So that's a little bit about number 1, about degrees and angles. Okay, the next thing that I need to talk about in our top 10 ideas is number 2. And this is called special angles. Special angles. And I'm gonna just name them: 30 degrees, 45 degrees, and 60 degrees. These are special angles. Now, let me just give you a little bit of rundown of where they come from. For example, if I took a square, and then I did a diagonal across here. That was a pretty messed up diagonal, but you get the idea, okay? So remember, this is a right angle, and these were right angles too, but this broken up into 2, so that must be 45. This angle must be 45, because they're equal, because of some properties of geometry. Now, notice what I have. I have a triangle, right? I have a triangle that's 45, 45, and by the way, if this side was 1, like 1 foot, sorry, and that was 1, this guy would be, according to the Pythagorean theorem, radical 2. So this is a special triangle, and we're going to use that special triangle a lot in the class. So, special person number 1, okay, 45, 45, 90 triangle, and those are the ratio of the sides. Now, another triangle that I want to talk about has to do with taking an equilateral triangle. Now, let's just try to draw an equilateral triangle. Of course, equilateral means equal angles, right? Well, lateral means equal sides. So all of these sides are the same. Now, we know that the sum of the angles in the triangle is equal to 180, so each of the angles had to be the same. 60, 60, and 60. Okay, that makes sense? Now, watch what I do. I'm going to take this brown line and draw an altitude, okay, of this triangle. Now, that means that's a right angle. Now, we know from geometry, hypotenuse, leg, we could play with it, whatever, that these two triangles are congruent. Now, let me just make believe this side is 2. Well, if that side is 2, this side has got to be 2, and this incomplete side has to be 2, but each of those has to be 1. Now, let's take this triangle out over here for a little walk, okay? All right, now remember, this was 60, this is my right angle, and you know that has to be 30. And we just said that the leg across from the small angle, that's this leg, this is a longer leg, and then this is the hypotenuse, okay? Hypotenuse. So the hypotenuse was 2, the short leg was 1, and the long leg is, I don't know, what is it? What is that side? Well, we know from the Pythagorean theorem that a squared plus b squared is equal to c squared. C is the longest side, the hypotenuse, so that's 2 squared. Let's just say that's, that's a. So a squared plus 1 squared, blah. Now we have a squared is equal to 4 minus 1, which is 3. So a has to be the square root of 3, obviously the positive part. Obviously the positive part. Whoa, that is a pretty serious eraser right there. Okay, so this is radical 3. Okay, So this is telling us that this other special triangle that we have, okay, is a 30, 60, 90 triangle, 1, 2, radical 3. We need to know that, and we need to remember that. So number 2, special angles in special triangles. Now before I go past this, I want you to know that we could take a coordinate plane and we could go 1 unit either way and we could draw a circle, okay? Now I'm going to draw an angle. So this is the initial side and this is the terminal side. Now you agree that I could use these special angles, like for example 30, this angle 45. I could go 60 this way, okay? This angle here is 60. I could go over here to this side here, okay? I could swing my angle over here and make that 30. I could do one here at 45. This is 45. And I could do one here at 60, okay? So this angle right here is 60. But remember, we always develop our angles from this 0 here. So really that would be 120, right? Because if that's 60 and 120, that has to add up to our 180. Does that make sense? Okay. Now I could continue that around the 30, the 45, the 60, the 30, the 45, and the 60. And I can take a circle and go all the way around and show all of the possible angle positions using those special angles. So I hope that was like special to you. Okay, let's talk about everybody's favorite. We're talking about the Pythagorean theorem. All right, so we are familiar with a squared plus b squared is equal to c squared. Now let's just kind of draw this out. Remember, this only works for right triangles, okay? I'll call that A, I'll call that B. And let's try to do this, make C always the longest side. So I could say C squared, the longest side, is equal to the sum of the squares of the other two sides, okay? Now here's a question. Could I find C if A is 3 and B is 4? That's a good question. So C squared is equal to 3 squared plus 4 squared. Oh yeah, well C squared equals 9 plus 16, which is 25. Take the square root, C is equal to 5. Yes, I can. C is equal to 5. Now you could use Pythagorean theorem in a lot of different ways, but the point here is that we're going to use this a lot in trig, and be mindful of that. Okay, what I want to do now is I want to talk about right triangle ratios. This is number 4. All right, so now what I'm going to do is I'm going to draw a little triangle here, okay? 3, 4, and 5. Now my question is can you name in this triangle all of the possible ratios? All of the possible ratios. So you're saying, oh yeah, I could do that. I've got 3 over 5, very good. I got 4 over 5, very good. I have, what else do I have? I have 3 over 5, 4 over 5. Can I switch this guy and have 5 over 4? Can I flip this guy and have 5 over 3? Yeah, I could do that. Let's see. Hey, what about 3 over 4? Could I do that? And then could I say 4 over 3? Now, folks, actually, these are the total number of possible ratios that you could get from that triangle. And guess what? The bottom are reciprocals and the top are just standard ratios, and they have names. The first one is called sine. Now, when I say sine, I mean sine of an angle. So I'm going to, like, this is my head and this is my hair. So I'm going to call this theta. Theta is the angle for that vertex here, A, okay? So sine of theta is equal to a particular ratio. It happens to be the opposite over the hypotenuse. When we say the opposite, we mean the opposite from that corner of the room. Okay? The opposite from the corner of the room. Now, we have another guy called cosine. Now, cosine of theta is another ratio. It happens to be this guy right here. And cosine is the adjacent means next to, over the hypotenuse, okay? So adjacent over hypotenuse. That makes sense? Okay, and then another one, the last one, is called tangent. Tangent of theta. Tangent is opposite over adjacent. So tangent of theta would be the opposite over the adjacent. That's where that 3 over 4 comes from. This is extremely, extremely, extremely important to get down. Now, so you know these guys, sine, cosine, and tangent. Now, just like these fractions at the bottom are reciprocals of the top, there are names of the ratios that you need to know. The reciprocal of sine is called cosecant, and that's H over O, okay? Like ho, 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 okay? And the one for cosine is secant, secant of theta. So that's H over A, ha, ha, ha. And so the other one is called cotangent, cotangent of theta, which is adjacent over opposite, AO. All right. Now, there's a way for you to remember these names, okay? People have different tricks, okay? You could think of an old phrase, sa, ka, toa, okay? All right, sounds like an Indian phrase. Sine, opposite over hypotenuse, cosine, so forth, okay? Or you could come up with the little phrase, saddle our horses, canter away happily toward other adventures. Isn't that exciting? Now, if you don't like that, hey, come up with your own. Now, so those are the names of the ratios. Sine, sine, okay? Cosine, cosine. Like co-signing a loan or co-signing onto a football scholarship. SEC, like SEC football. That goes with cosine. And then the gentleman at the beach, the tangent, get it, tangent. He stayed too long at the beach and got a bad burn, had to go to the hospital. They sat him on a cot, okay? All right? People have their different tricks to know these. So know the right triangle ratios. There are 6. But I'm going to call, instead of Big Ten football, I'm going to call the Big 3. Make sure you know them. I'm going to call this standard position. Now, what in the world is standard position? Well, it means you have an XY coordinate system and you have an angle right here. We already talked about this. This is standard position of an angle on the coordinate plane. Now, a couple things you need to know. First of all, you need to know if the angle opens this way, it's a positive angle. And if the terminal side right here, right, if we move that down, okay, like down here, okay, that is a negative angle. So be mindful of that, positive and negative. Now, another word that comes up in trigonometry a lot is coterminal. Coterminal. Well, co-ed means boy and girl at the same place. Coterminal means angles at the same place. So let me give you an example. Let's just say I have, here's an angle, and let's just say it's 30 degrees. 30 degrees. Now, that's kind of a cold angle, but by the way, if you're cold right now, just get in a corner of the room. Just get in a corner of the room, because, hey, it's 90 degrees, right? Okay, little joke there. All right, so back to our regularly scheduled, important stuff here. So this is 30 degrees. Now my question is, what if you went and you did an angle not 30, but you went, wow, look at this. You went all the way around 360 right here and then did 390. So this red thing represents 390 degrees. That's a hot angle. Now, does everybody agree that if I drew the terminal side, it would be right over the other guy? That's right. Co-ed, co-terminal. Those are two angles that have the same position on the we're going to call it the circle. All right, now let me explain this another way of coterminal. You remember King Arthur, and he had a what? What kind of table did he have? That's right, he had a round table. Now, for lack of drawing ability, I'm just going to go around and just put seats here. These are seats around King Arthur's table, okay? And let's just play make-believe for a second, okay? And make-believe, they're all the same. They're 360. And here's where you are, okay? Now, let's just say that you were at the 30-degree position. Now, where would you be sitting? Okay, so again, I'm just going to go like this. This is 30 degrees, okay? If I asked you to leave and come back and go to the 390 position, where would you be? You would be in the same seat, okay? So just remember, there's only 360 seats, and you can only be in one seat and got to sit in it completely. That is the idea of coterminal angles, and I hope that makes sense to you. Now, what if someone said, find the angle that is coterminal with 750 degrees? How do I do that? Well, I'll tell you how you do it. What you do is you just keep traveling around the table till you find that seat, go in there and, look under the label and name the seat. Another way to do this is, hey, just take away 360. If I take away 360, it's at what, 390? Okay, let's take another 360 away, and that is 30. Oh, lo and behold, I am really at the 30-degree seat in King Arthur's Round Table. So be mindful of that. Now someone's going to say, how in the world am I going to do it if it's like a negative degree? So negative 380 is like, right? Okay. Well, just keep adding 360. By the way, if I added 720, wouldn't I get 80? Okay. So 80 degrees. That is the position here. 80 degrees is about, you're right before 90, not as hot as 90, okay? But we're warming up to that idea. So please know coterminal. Let's see. Now there's one more thing that I need to talk to you on this particular video. Okay, that was exciting. All right, now the only thing I need to do is I need to talk about a reference angle. Reference angle. Now, what a reference angle is a shortcut way of knowing the angles around the unit circle. Okay, coordinate plane, 1 unit long, circle going around, 1 unit radius everywhere, okay? Now, hey, watch this. So if I draw a terminal side here, and this angle is 30 degrees, I could do one over here, okay, that looks like the same. But now hold the phone for a second. This is 180, right? And if that angle was 150, can you tell me what this little angle is right here? In school it's called linear pair, but that may be a, not mayor going back to school, but you take any two angles, add up to 180 degrees. I think of school years, okay? 180 degrees of school, and you got to eat your supplementary tablets for, supplementary angles or whatever. All right, so this is 110 degrees. Now, the point being is that a reference angle is an angle formed by the terminal side and the plus or minus x-axis. Let me say that again. A reference angle is the acute angle formed by the terminal side and the x-axis. So let me come up with another one here. Okay, this is 60 degrees. This means that's 60. This is 120. 120. This means 120. Now the question is, I want to know what the reference angles are. Well, this angle, an acute angle, we've already reviewed that, okay? So this is 60, we get that. What in the world is this angle? Very good question. The only x-axis part I could use, it's a ray of the x-axis, okay, is this angle right here, okay? How do I figure that out? Well, you could just subtract, okay? So there you go, 60 degrees. Reference angles are very, very important. So please know how to figure reference angles on the unit circle. That would be very helpful. Start using radian conversion, okay? Or using radians, and then first of all, we're going to talk about converting. So here's an idea. 270 degrees, I want to convert that to radian. Well, just remember the little conversion chart I gave you. 180 degrees equals pi radians. Now, there are 14 ways to do this. Here's how I do it, and it seems to work for most people. I make these little conversion charts. And I'm going to put 180 degrees here because that's the only way the units are going to divide out. I'm going to go mark them out. You can only mark out when you have them across each other. And by the way, I can mark a 0 out, right? And by the way, 9 goes into that 3, 9 goes into that 2. So this is 3 pi over 2, or 3 halves pi. They mean the same thing. Now, you could actually, get the plug in 3.14 and get a decimal answer if you wanted to. Now, this answer is called leaving it in terms of pi, How am I going to convert this radian angle to a degrees? Well, I'm just going to make my bar, my chart right here, and I'm going to put my pi over here. Remember, we're just using this simple formula. Don't make it hard. Okay, now when you do this, these play wipeout. 3 goes into 180 60 times, so it's just 4 times 60, which is 240. 240 degrees. Notice that we were able to convert. In this particular case right here, okay, right here, we converted from degrees to radians. And then down here at the bottom, we converted from radians to degrees. So this is an important aspect of using radian measures, and in this particular case, we're calling it converting. All right, now what we need to do is we need to use some of these ideas. So I'm trying to get my little guy back over here. So I have, what am I going to do? I'm going to talk about angular velocity. Angular velocity. So what I'm going to do is I'm standing here and I have a string with a little washer at the end, and I'm going to twirl this around, twirl this around, twirl this around, twirl this around. Okay? Now, you agree that this angle is changing over time. Okay? If I twirl it faster, then, the angle's going faster. Now, this is this formula. This is called angular velocity. Angular velocity. This is my angle. Normally it's in radians over time. A lot of times this is in seconds. Now, you actually are familiar with this because you have seen these words before. RPM. What does RPM mean in a car? It means revolutions per what? Minute. Okay? So you're familiar with that. I certainly don't need to go rounds with you on that. Sorry about that. All right, now, perhaps you were a very, I don't know what you call it. You have a sibling, that you're holding on to, okay, and you're twirling them around when you're younger. Hey, don't let go. All right, so that is really torturous. I would never do that. But you're familiar with that. Now, so let me ask you a question. If something's going 2 radians for every 1 second, what is this angular velocity? Angular velocity is just 2 over 1, or 2 radians per second, or 2 radiuses per second. That makes sense? Now, What's going to happen to your younger sibling if you're twirling them around real fast and then you let go? What is going to happen to young Susie over here, okay, is that she's going to, when you let go of her, she's going to fly that way, okay? And that would be a very unkind thing to do. But we're going to use this formula. V is equal to R times omega. What am I talking about? You are going to convert angular velocity to linear velocity. Linear velocity, okay? Someone says, I'm not getting it quite, but I'm kind of getting it. I go, I know, sometimes I get tired of that, but okay, well, that's all right. So here's a tire on a car, and you got behind some kind of dump truck, and they laid a lot of rocks on the ground. You got a rock stuck in your tire, and you say, I'm going to go around that dump truck because I don't want to get my windshield killed. So you go around the dump truck, and that little stone flies out of the back of your car because the force of sticking it in the tire, outweighed whatever, okay? So that rock went out. That could hurt, okay? Now that rock speed is based upon two things: the size of your tire and how fast your tire was going around. Am I making any sense? Yes, I am. So what if the radius of your car was like 1 foot and it was going around like 30 feet per second? 30 feet per second. How fast would that rock be heading to someone that's right behind you? Well, the linear velocity would be 30, 1 times that, 30, 30 feet, and then 30, well, we're going to have to say revolutions per second, 30 revolutions per second. So it would be 30 feet times revolutions per second. Well, seems like we're missing something, and we are. So here's the key to working these problems. 1 revolution is 2 pi radians. Remember, pi is half, so if I go all the way around, that's another pi. So besides getting a full stomach, it's 2 pi. So 1 rev is 2 pi radians. 2 pi radians. So we're going to have to multiply that. 2 pi radians is 1 rev. And so these revs cross out, and lo and behold, I would have 60 pi feet per second. Okay? Keep that in mind. Keep that in mind. That's really like 180 feet per second. That could be something pretty fast. So this is an application of radians. Added to the other one is just simply, remember, angular velocity, linear velocity, but don't forget this little formula over here that will help you as well. Now, there is one last one that I need to give you. Here it is right here. I noticed this in your book as well. So, we're talking about, I've got to get my silly pen to work here again. Okay. All right, here it is. The area of a sector is equal to 1/2 r squared theta. Okay. I'm not promising anything, but I will try to have the formula on your formula sheet for you. First of all, what in the world is a sector? A sector, okay, is a piece of pie of a circle. So this would be a sector. It's kind of like playing Trivia Pursuit, right? All right, so this is dumb. Let's say this is 1 foot, and let's just say that angle in radians was 1.5 radians. Can I find the area of this region right here? Remember, this is in radians. Well, yeah. 1/2 r squared, 1 squared, times the angle in radians. So this would be what? 0.5 times 1 times 1.5, and that would be 5 and 2.5, or 7.5. And if that's feet, it's going to be square feet. Okay, so just remember that. Now, a little bit of warning. Some of you guys may say, oh, I saw that in high school. The teacher did this. Okay, and we had to find this area. Okay, that is not a sector, that is called a segment. Okay, a segment. So with that segue, I'm going to move on to number 7. Okay, all right, we're calling this one, this special idea, the unit circle, and particularly the unit circle angles. So what I'm going to do is, let's see, let me take a black here, okay? Okay, now remember, we're going to put a circle over here with a unit 1 length. Okay, so in theory, I just messed up. Let's see, can I get the little pointer? Pointer, 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 pointer. Oh, I have no idea. Okay, we're gonna stop. Okay, sorry about that. So now the unit, okay, so this is 1. This is 1. This is 1. This is 1. Matter of fact, the ordered pairs are all these 1, 0, right? This is 0, comma 1. This is negative 1, comma 0. We're using the coordinate plane. 0, comma negative 1. Okay, but you get what I'm talking about. Now, we're going to go around the unit circle, and let's just do degrees first. We're going to do degrees first. Okay, so let's just take a number. Let's take a color. All right, 0 degrees, 90 degrees. This is 180 degrees. This is 270 degrees. And all the way back up here, if I go all the way back over here, that's 360 degrees. Now, remember, this is the 45. So this guy right here would have to be 135. This guy is 45 plus 180, which is 225. This would be 45. That would be 315, or 45 away from 360. Now, let's go up by 30s. Mr. Staples, what do you mean by 30s? I'm going to go up 30. Okay, 30. I'm going another 30 degrees. Okay, that's right here. That's 60, right? Another 30. I'm going another 30. I'm going to hit 90. Okay, we already got that guy. Another 30 degrees. I'm up here at 120. Another 30 on the unit circle. I'm at 150. And then another 30. I'm at 180. Let's go another 30. I'm stopping right here. So this angle is, I'm looking at the time, I'm doing okay. So this is 210 degrees. Another 30 is going to go down here to, what is that, 30? 240 degrees. And I'm going to go another 30. I'm going to hit right over here at 270. I'm going to go another 30. I'm going to end up over here. That's going to be 300 degrees. And then I'm going to go another 30 degrees. I'm going to end up right here, and that's going to be 330 degrees. And another 30, I'm going to end up here at 360 where I ended up. So I could go around the unit circle in degrees. Now, here is the $30 million question. Can I go around the unit circle in radians? In radians. Well, I'm going to start right here. I want another color. Give me the right color. Here we go, right here. So that's 0 radians. I'm going to go all the way around to here. That would be pi radians. I'm going to go halfway that distance, so that's going to be around pi over 2. Then I'm going to go another half pi, and this part down here is going to be, well, 1/2, 2 halves, 3 halves, so it's going to be 3 pi over, what am I going to do? I don't know, can I erase this? Okay, I'm not that good at this. That kind of looks pretty good. All right, so this is 3 pi over 2. Let's go another half a pi, so that's going to be 2 pi, okay, or a full stomach. Now, let's go half of the pi over 2. Well, that's going to have to be pi over 4. Let's go half this way. That's going to be 3/4 pi, or 3 pi over 4. Let's go halfway here. That's a pi and a fourth, which is what? 5 pi over 4? And then let's go over here, a fourth. This is just shy of 8 pi over 4, so we're going to call that 7 pi over 4. Okay, now let's do like we did with the 30 degrees. Let's do like we did with the 30 degrees. If I go 30, that's just pi over 6. Another 30 is 2 pi over 6, or pi over 3. Another 30 is a 90, we're okay. Another 30 is 4 pi over 3, 4 pi over 3. Another 30 is, well, actually, that reduces to, that was 4 pi over 6, or 2 pi over 3. Okay, hold the phone here. Okay, watch how I do this. Pi over 6 is 30. Here's 1. Here's 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 7 pi over 6, 8 pi over 6, that reduces to 4 pi over 3, 9 pi over 6, which we got that guy, 11 pi over 6, no, what am I doing? That was 9 pi over 6, 10 pi over 6, which is 5 pi over 3, 11 pi over 6, 11 pi over 6, watch how you write that, and then 12 pi over 6, which is 2 pi. So, anyway, I hate to go rounds and rounds about that, but this is a way to understand the angle measures around the unit circle, and this is very, very important to get down. So practice that. Now, I gave you a little handout. It's called the unit circle blank, and I would just practice that till you get that down. That should be really, really clear in your mind. And that is one of the reasons why a lot of people don't do well in. Let me say that again. That is one of the reasons why people don't do that well in trig, is because they don't have this down. And if you'll do that, that will help you out. I hope that helps you. Okay, folks, what we want to do is we want to talk about the unit circle values. The unit circle values. So let's get to looking at this. Okay, so I'm getting a little bit better with my line drawing here. Okay, we need our circle. Let's try to do a good circle. Okay, we're talking about our unit circle values. Now, we got to put some, let's put some angle numbers here. Remember, this was 0. This is 30, 45, 60, and 90, okay? All right, now another thing that we need to do is we need to remember those two special triangles. You remember? Okay, 1, 1, radical 2. 1, 1, radical 2. Now, if we divide everybody by radical 2, I'd have 1 over radical 2, 1 over radical 2, and 1. See that? Okay, let's take the other triangle here. Let's see, that was 1, and that was radical 3, and that was 2. All right, what if this side was 1? We'll divide everybody by 2. Just divide everybody by 2. 1, 1 over 2, and radical 3 over 2. Okay, so what we're going to do is this hypotenuse is really going to be the radius on the unit circle. Okay, remember this angle is 45. This angle is 30. Okay, all right, well, enough said there. Now, what we want to do is we don't want to talk about angles, we want to talk about values. And if we'll just do quadrant 1, this is quadrant 1 right here, right? Okay, then we could figure out the other quadrants. So let's start with some serious working here. It's the unit circle, so that has to be 1, 0. It's the unit circle, so that angle right here, that location on the unit circle has to be 0, 1. This has to be -1, 0. This has to be 0, -1. That makes sense, right? Okay, now let's go to the 45 degrees. The 45 degrees. You see this angle is 45 degrees. And by the way, if I put a point there, don't I have a right triangle? A right triangle right here, okay? Now, we already know that the right triangle, that's a 45-degree triangle, looks like this guy over here. Now remember, I could shrink it and it's still proportional. So I shrunk it down to this side. And notice that this radius of 1 is really this hypotenuse. So now my question is, remember we have x, y all the way around this unit circle. So my question is, what are the values for x and y over here? Well, x is the distance from the origin to this location. So that's going to be the bottom of this triangle. That's 1 over radical 2, or radical 2 over 2. And the y is going to be this side right here, which is going to be the same. So that's radical 2 over 2. That's not that bad. Now, let's go and look at the 30-degree angle. The 30-degree angle. Well, here's my one side. Here's my point on the unit circle. I need to find out what the values are. So this is the long leg, that's the x, and the y is the short leg. Now we could look at this triangle, but it's 2 for the long side, the hypotenuse. So that we shrunk it down by into this triangle, which makes a lot of sense. So again, this is the short leg, this is the hypotenuse, this is the long leg. Well, we already know that's 1 because it's a unit circle. So the y is 1/2 and the x is radical 3 over 2. Well, let's just write that in here, okay? So the x is radical 3 over 2 and the y is 1/2. All right, now let's do this. Let's go and figure out the 60-degree angle. Well, lo and behold, the 60-degree angle gives us another orientation of that 30, 60, 90 triangle, that special triangle, which I've been warning you guys you need to know. So the x is the short leg, which is 1/2, and the y, this up and down right here, is the long leg, which is radical 3 over 2. Okay? Now, you have now all of the values of the unit circle in quadrant number 1. Quadrant number 1. Can I find all the values in quadrant number 2? That is a good question. Okay, so here we go. Now, let's do the 45 first because that makes a lot of sense, right? Can I draw this down here and have a reference angle of 45 degrees? That's going to be negative radical 2 over 2 and radical 2 over 2. Why is that? Because here the x is positive, the y is positive. In quadrant 2, the x is negative and the y is positive. Now we can actually sort of copy the values over from quadrant 1. So this guy right here at 120 degrees would be negative radical 3 over 2. Remember, the x is negative and the y is 1/2. This, now keep in mind, look, this is the longer leg is the x, so it's going to be negative radical 3 over 2 and 1/2. Okay? So you're halfway around the unit circle with the values. Can we do the rest? Answer is we can. Now remember, here the x's are negative and the y's are negative, and here the x's are positive and the y's are negative. So you could do this a different way, a bunch of different ways. Here you could write negative radical 3 over 2. you could write radical 3 over 2. Here you could put negative 1/2. Here you could put negative 1/2. Here you could put negative radical 2 over 2. You could put the y as negative radical 2 over 2. Down here you're going to have, you're dealing with this angle, so you're forming a 30, 60, 90 triangle. This is the short and this is the long of it. So that's going to be negative 1/2 and negative radical 3 over 2. And then this is going to be what? This is going to be this triangle where the x is short, so that's going to be 1/2, but the y is going to be negative. And then this is the radical 2 over 2 and the negative radical 2 over 2. So this video are all about values. As I go around the unit circle, I want to know at these special points, using those special angles, what are the values of x and y. Now we're going to use these ideas a lot later. The biggest idea is forming the essential sinusoid graph, which will be helpful. And we'll come back and we'll maybe put some decimal values to these numbers to make it make sense to you. So please keep that in mind. All right, now here's a little trick that you could use if you want to. You could think of quadrant one as all, quadrant 2 as students, quadrant 3 as take, and quadrant 4 as calculus. Okay, all students take calculus. We're going to use this idea later when we talk about sine, cosine, and tangent, and maybe you can get something from that. Maybe I shouldn't have talked about the all students take calculus right now, but I get excited about this trig because, well, you could do a lot with it, and it also is a subject area that a lot of people get stuck on, and it's like they're going around and around and around and around and around, and you know, they just, I'm not getting anywhere. I don't want that to happen to anybody. So this is top idea number 8, the unit circle values. Okay guys, what we're going to do here is we're going to talk about trig values of any angle. And we're going to start with a very simple problem. Could you please tell me all the 3 major trig ratio values of 30 degrees? Of 30 degrees. Well, this is a combination of the unit circle and our special triangles, So let's see. Hey, 30 degrees. Remember, this was 1. This was 1/2, and this was radical 3 over 2. Okay, this side right here. So my question is, if this is theta, this angle is theta, the sine of theta, so the sine of 30 degrees. I want to know the cosine of 30 degrees. I want to know the tangent of 30 degrees, okay? Well, let's see. The sine of 30 is just, remember, it's opposite over hypotenuse, then adjacent over hypotenuse, then opposite over adjacent. So you're like theta man, okay? You're a theta man, and you're in this little corner right here. So sine is opposite. 1/2 over 1 is just 1/2. Cosine would be radical 3 over 2. And tangent would be, what would that be? That would be 1/2 over radical 3 over 2. But another way to do that is just use this basic triangle I talked about before. Okay? Remember, they're similar triangles. So tangent would be opposite 1 over radical 3. 1 over radical 3. But in trig, we like to make things difficult, so make sure that you rationalize that radical 3 over 3. Okay, you multiply the top and bottom by radical 3. Now, these are the 3 trig ratios of that angle. So please, please, please keep that in mind. All right? Okay, now I have seeing that we're probably missing something here, and I want you to be upset. Okay, remember how 45, 45, it was 1, 1, radical 2? Remember, this is 45 degrees. And remember how 30, 60, 90? This was 1, this was 2, this was radical 3. Remember, this is 30 and this is 60 degrees. Okay? And remember, you're theta man or woman, okay? Now, what we want to do is we want to fill out this chart. This will probably help a lot of you guys. So we're going to do the 30 degrees, we're going to do the 45 degrees, we're going to do the 60 degrees. I want to know what sine of that theta is. I want to know what cosine of that theta is. I want to know what tangent of that theta is. This will probably help you out. Okay, well, let's do sine. Sine of 30 degrees is, I'm over here, okay? I'm over here, and opposite over hypotenuse. Well, that's 1/2. Sine of 45, that's radical 2 over 2. Sine of 60, well, now I'm over here. Opposite would be radical 3 over 2, okay? All right, let's do cosine. Cosine of 30, so remember, I'm right here. It's going to be adjacent over hypotenuse, radical 3 over 2. Cosine of 45, well, here's 45. Cosine would be adjacent over hypotenuse. Well, that's square root of 2, okay? So 1 over radical 2 or radical 2 over 2. I make mistakes. And then cosine of 60. Now remember, I'm over here, okay? Theta man's over here. So cosine is adjacent, which would be 1 over hypotenuse. So 1/2. Okay? So notice this little chart. Now tangent of 30 degrees. Tangent is opposite over adjacent. So radical 3 over 3. Let's go to 45 degrees. 45, tangent is opposite over adjacent, which is 1. And then 60 degrees, again, you're angle man, okay? You're in there, the corner of that room right there. Opposite over adjacent is just radical 3. So please keep this little chart in mind when you're going around the unit circle with those special angles. That could help you out very, very much. Question that gets people, and the question is, find the trig values of any angle. Now I'm going to give you a little, like, I'm going to give you a little formula here. X is just r times cosine of theta, and y is just r sine of theta. I know someone's going to scream, why is that what's going on there? I go, look real quick, okay? If this is any kind of x and y, this is y, this is x, this is r, right? Radius. So sine of theta is opposite over hypotenuse, which is y over r. So that means that y would equal r sine theta. Enough said, here we go. All right, the question is, I'm giving you a point. You got to find the trig values of all functions. Wow, that is something else. First of all, what quadrant is that in? The point 3, 4 is right here, right? So what I'm going to do is I'm going to draw a little triangle here, okay? Remember, this is 3, -4. All right, now watch what I do. It's a right triangle, and this is 3. And then this side of the triangle is 4, because it's the x and the y value. And because the Pythagorean theorem, this is going to be 5. Now also try to remember, I gave you a little hint. All students take calculus. What in the world does that mean? Good question. I'll tell you exactly what it means. What it means is all of them are positive in quadrant 1. Students, only sine is positive, everybody else is negative. All students take, tangent's positive, these guys are negative. Calculus, this is positive, these guys are negative. So remember, I want you to find the trig values of all of the ratios for this particular location. So I'm going to use this idea when I, write my answers. Question number 1. Let's do sine of that angle. Sine of what angle? sine of this angle right here, okay? All right, so this is my reference angle, and this is really my angle. All right, so I'm going to do sine. Sine of theta is equal to opposite, which is 4, over hypotenuse, which is 5. Cosine of theta is equal to adjacent, which is 3, over hypotenuse, 3 over 5. And tangent is just opposite, so it's 4 over adjacent, which is 3. 4 over 3. Now remember, the cosine's positive, and the other guys are negative, okay? That's one way to do it. There are many other ways to do it. That's one way that is what would work. Now here's a dumb question. What's cosecant of theta? Well, it's the reciprocal of the sine. What's SEC football of theta? That's just going to be 5 over 3. And what's cotangent? Okay, that's going to be negative 3 over 4. Okay, so that's a way to find the trig values of all the ratios of any angle given a particular point. And that's it. Okay, we're going to talk about graphs. But before we do that, what we want to do is I'd like to see if I could just draw. Okay, that's cool. So we'll come back to that. Now, something else I want to do too. Okay, now pay attention to the little picture down here at the bottom. Okay, now I have no idea what happened to my pen. Okay, here we go. We're going to go around the unit circle, and we're going to do the graph of y is equal to sine of theta. Okay, we're going to start at 0, and we're going to end at 360. 0 to 360. Now remember, this is 180, and this would be 90, and this would be, 270. Okay? All right. Now, if I go around the circle, notice that the sine starts off at 0 right here, and it goes up to 1. So the values of the y start at 0, go up to 1. Then notice the sine of the y values go down to 0 here. So let's do this. Let's graph this. It goes up to 1. Let's put some values in here. 0 degrees, the sine is 0. At 90 degrees, the sine is 1. Okay, at 180, the sine, which is the y, is 0. Then at 270, well, let's go down here. At 270, the y value is -1, so I need a -1 here. So 270, -1. And then what happens to the value of the y as I go back to the 360? Well, it goes back to 0. That makes sense? Now, notice what I do in my little illustration. I've got 0, I've got 90. So 0, there was no height. At 90, there was this height. I'll pick a different color. Okay, now notice what's happening at 30. At 30, it's this tall, which is 1/2. At 45, that converts to 0.7. And at 60, that's 0.86. So I could actually go over here and put those points in here if I wanted to, okay? Now let's go to 120. Well, let's go halfway. This is 0.7, so halfway 0.7, that's like about right here somewhere. No, Mrs. Staple just messed up, okay? All right, just disregard that point. And 150, the y is going to be 1/2, so 150 is before 180, so 1/2 is about here. Okay, here's my point, no pun intended here, okay? You can copy these, you can copy and know what's happening along all the way around the unit circle. Here, the y values are getting taller till 90, then they start getting smaller Okay, so I could fill in this part of my sine curve. Now what's going to happen down here at the bottom? Well, we know that the 270 is right here. It's going to happen at every point along the unit circle. The y values are getting smaller to -1, and then they go to 0. Okay, so this curve is representing the graph of the function y equals sine of theta. This is theta, and these are the values of y. That's a basic graph, and we could expand upon it to do the cosine and the other one as well. Okay, what's going to happen with the cosine? Remember, the cosine are the x values. At 0 degrees, they're 1, right? At 90, they're 0 because the values of cosine get smaller and smaller. The x's get smaller. At 180, it's all the way over here to -1. So from 1 to -1, okay? And then as I go around the unit circle, they get bigger to -1, then they get smaller, then the values get bigger all the way back to 1. How would I do that on the graph? At 0 degrees, cosine is 1. At 90, the x value is 0. At 180, it's -1. 270, it's 0. And at 360, it's 1. So can I graph that function? Yeah. So the cosine function looks like this. Again, you could plug the values back in there, okay? So this curve is representing the cosine curve. Now it continues that way and continues that way, all right? The only difference between these two curves is the sine curve starts at the, like the bottom of the wave, okay, or the beginning of the wave, and the cosine starts at the top of the wave, kind of like some guy, on a surfboard, okay? All right, so keep that in mind. Here's your x, and here's your y. I hope this little video gave you some idea of how the graph of sine and y equals cosine of x work. It is very important to get those two, and they are used to model an endless number of things. I do hope that this video helps you.